Good evening, fellow engineers. My name is Roberto Sainz, and today I will be discussing an energy analysis project on a polymer electrolyte membrane fuel cell for a passenger vehicle. This project has been prepared for the UT Tyler Mechanical Engineering Department by my partner Brittany Fink and myself. The agenda for this presentation will be the introduction, followed by motivation and key objectives, background, benefits, drawbacks, analysis, references, and lastly, the appendices. Firstly, what is a hydrogen fuel cell? A hydrogen fuel cell is a power source that generates electricity through an electrochemical reaction by oxidizing hydrogen. In an ideal setting, the byproduct of this reaction is water when the hydrogen bonds with the oxygen and heat. Since water and heat are the only byproducts, fuel cells are theory to be very environmentally friendly compared to fossil fuels. The problem with fossil fuels is that when combusted for energy, harmful chemical byproducts are released into the environment. If more hydrogen fuel cells were used, we could reduce greenhouse gas production, which could in turn help reduce climate impact. Furthermore, fossil fuels also produce less energy per volume than a typical hydrogen fuel cell. The motivation to analyze the hydrogen fuel cell came from a variety of interests. Hydrogen fuel cells have a much higher energy to weight ratio than lithium-ion batteries. Implementing them into vehicles would reduce wear on both the road and vehicle, and the reduced weight would make the vehicle easier to handle. Hydrogen fuel cells can also be refueled in a matter of minutes versus a lithium-ion battery, which requires hours to recharge. A large factor for myself is that hydrogen can be found in a plethora of environments, so it is the only element that exists as a single atom. It is easiest to bond across our universe. This also opens up the possibility of using hydrogen as a fuel source during space exploration. There are several key objectives that we hope to accomplish with this project. We will be conducting an analysis that shows how variances in fuel input, oxygen input, and temperatures affect the performance of the fuel cell. We will represent this fuel cell model by simulation using MATLAB. We will also assess the cost and maintenance between a fuel cell vehicle, Toyota Mirai, and a Tesla lithium-ion battery-powered vehicle. We will also address some environmental impacts. As stated before, hydrogen fuel cells create electricity by an electrochemical reaction that oxidizes a hydrogen fuel source and only produces water and heat as byproducts. If a hydrocarbon is used as a fuel source, the reaction will also produce carbon dioxide along with water and heat. Hydrogen fuel cells have two plates, the anode and the cathode, separated by a polymer electrolyte membrane, or PEM. Hydrogen fuel is inputted at the anode side and oxidized on the cathode side with oxygen. As the hydrogen cations travel through the PEM, the electrons are removed from the cell through an external circuit. The hydrogen cations oxidize at the cathode to form water molecules. There are 5 types of fuel cells: a solid oxide, molten carbonate, phosphoric acid, proton exchange membrane, and an alkaline fuel cell. We decided to pursue the proton exchange membrane, or PEMFC, because it is ideal for a passenger vehicle. A PEMFC operates at relatively low heat, and the PEM has a durable electrolyte that isn't sensitive to carbon dioxide that may become present in the reaction during operation. Benefits, as stated, if done correctly, there's no harmful chemicals, and it is also highly efficient at 40 to 60% compared to a combustion engine, which is 30 to 35%. Drawbacks of the system is that it is a newer technology, therefore it is currently very expensive to produce. Also, the main source of hydrogen gas is from methane, and we obtain that through a system called steam methane reforming. And in doing so, this process produces a lot of carbon monoxide and carbon dioxide, which are common greenhouse gases that do affect the climate. They do have a climate impact. Before we can begin this problem, before we can begin our fuel cell analysis, we must set some assumptions. These include We're going to use ideal gases. The fluids are incompressible and inviscous. There's no external work done on the system, no friction or fouling in the piping of the system or ducts. The system is at steady state operation and it is operating at STP, which is standard temperature and pressure. At the anode, the hydrogen fuels protons and electrons are separated. The hydrogen cation travels through the proton electron membrane, while the electrons are transferred through a wire as electricity to a peripheral or battery. At the cathode, the hydrogen cations react with the oxygen supply to produce liquid water as a byproduct, since we are operating at under 100 degrees Celsius. Fuel cell efficiency can be calculated by multiplying three major efficiencies of a fuel cell system together. The three efficiencies pertain to the fuel cell's thermodynamics, voltage losses, and fuel utilization. These efficiencies will be described individually throughout the presentation. Fuel cells are very thermodynamically efficient, but as in every reaction, there is energy lost by heat. The thermal efficiency of a fuel cell can be calculated easily by dividing the reaction Gibbs free energy difference by the change in enthalpy of the reaction. Gibbs free energy difference was supplied in the textbook for liquid water, but the change in enthalpy needed to be calculated. The enthalpy of the reaction can be calculated using the following equation. The enthalpy values were gathered from the thermodynamic tables, and the number of moles of each reactant and product is determined from the chemical balance equation. This equation yielded us an enthalpy reaction of 285.83 kilojoules per mole. We plug this value back into our thermal efficiency equation with Gibbs free energy difference. This yielded us a thermal efficiency of 83%. The next efficiency we will be calculating is for voltage, is the voltage efficiency. The voltage efficiency of a fuel cell is dependent on build requirements of the fuel cell itself. Electrolyte thickness and porosity in ducts are a few of the factors that can affect the fuel cell's performance. Before we can begin analyzing the system, we have to define some variables regarding the system. These variables will be described as we go, but the important ones to mention at the moment are the steady state and standard temperature and pressure operation. That being, we're at atmospheric temperature and pressure, as well as a steady state current density of 10 milliamps per centimeter squared. We start by calculating the voltage output of our PEMFC. The real voltage can be calculated by subtracting the voltage losses from the theoretical thermal voltage output. These equations will be described in the following slides. The theoretical voltage can be calculated by dividing the negative of Gibbs free energy difference by the number of electrons multiplied by Faraday's constant. Gibbs free energy is referenced through the textbook and is temperature dependent. This equation yielded us a value of 1.229 volts. But to get the actual voltage, we must start subtracting the system's voltage losses. The first of the voltage losses is the activation voltage loss, or activation over voltage. This is an energy used to prep the electrolyte for chemical reactions to occur. To solve for overvoltage, we'll be using the Butler-Volmer equation. This equation is a bit complex, but it will be simplified after considering the parameters of our theoretical fuel cell. The first parameter to address is our alpha. Since our alpha is equal to 0.5, the equation is symmetrical. This means the reaction is symmetrical, This means that forward and reverse currents are identical and only one side needs to be analyzed. The second condition is steady state, meaning there is no change in current density occurring. JSS is equal to J. This simplifies to the equation below. The simplified Butler-Volmer equation can be solved relatively easily. As you can see, the activation over voltage is temperature and current related. Higher operating temperatures and current densities will require a higher activation voltage loss. All variables are known or given, and a final value of 0.473 volts is calculated. The next voltage loss to calculate is the charge transportation losses across the electrolyte membrane. This equation introduces a new variable, the area-specific resistance, or ASR ohmic. This variable can be calculated by dividing the membrane thickness by the membrane conductivity. Both of these values are given in the system parameters. This produces an ASR of 0.1 ohms centimeter squared. With this variable known, we can continue to the transportation voltage loss equation. This is solved by multiplying the current density and the ASR ohmic. This provided a loss of 1 millivolt. The last voltage loss to calculate is the voltage loss due to reactant depletion in the catalyst. This equation is shown below. As you can see, there is an unknown variable for limiting current density, JL, that we must calculate for. The limiting current density can be solved using the following equation, which introduces another unknown variable, DEF, efficiency, or effective diffusivity. This can be solved with the following equation, which presents itself with another unknown, the nominal diffusivity of the catalyst, or Dij. The nominal diffusivity, or binary diffusion coefficient, can be calculated using the following equation. It is a busy equation, but all variables are known or can be referenced through literature. As you can see, this equation is dependent on critical temperatures, pressures, and molecular weight. The parameters A and B are specific to this equation, which is based on the kinetic theory of gases at low pressures. After plugging in all values, we get a binary diffusion coefficient of 0.810 centimeters squared per second. With our nominal diffusivity known, we can plug it back into the effective diffusivity equation that is based on Bruggermann's correction. In this equation, multiply the nominal diffusivity by the porosity of the electrode raised to a power of 1.5. The porosity of the electrode is the ratio between pores and total volume on the electrode. This equation yields us an effective diffusivity of 0.205 centimeters squared per second. With our effective diffusivity known, we can calculate our limiting current density. The limiting current density, JL, is the condition that will occur when reactant concentrations in the catalyst drop to 0. This represents the highest current density the fuel cell could physically reach. All factors have been used before except the bulk flow reactant concentration, CR, and the electrode thickness. With these parameters plugged in, we yield a limiting current density of 5 amps per centimeter squared. Now that we know our limiting current density, we can now calculate the voltage losses due to the reaction depletion in the catalyst. In this equation, C is the geometric concentration loss coefficient. After plugging in values, we obtain a voltage loss of 0.2 millivolts. Now that we have all of our voltage losses calculated, we can return to the original equation to obtain the actual voltage of the fuel cell. After plugging in the fuel cell voltages to the equation, we get an actual voltage of 0.755 volts. Plugging this back into the voltage efficiency equation, our actual voltage, V actual over E thermal, we obtain an electric efficiency of 61.4%. The fuel utilization can be solved with the following equation. In the numerator, we have current divided by the number of electrons and Faraday's constant. In the denominator, we have the hydrogen fuel rate supply given in moles per second. Current can be found by multiplying the current density by the area of the electrolyte. For our theoretical fuel cell, we use the fuel utilization of 95%. Now that we know our various efficiencies, we can multiply them together to determine our fuel cell's total efficiency. When doing so, we got a total efficiency of 48.4%. The values we obtain from our theoretical fuel cell vary a bit from what a typical PEMFC should produce. A typical fuel cell usually produces an actual voltage within a range of 0.4 to 0.7 volts. Ours produced 0.755 volts, which is slightly higher than the typical. The efficiency of our system is within the range of a typical PEMFC though. I believe we can achieve better performance from our fuel cell if we operate at a slightly higher temperature. We have begun MATLAB simulations, but haven't made much progress to present at the moment. Okay, this is a list of our references, and I just want to say thank you for listening to my presentation. I hope you enjoy the rest of your day.